Okay, folks, I'm going to start from the top. I apologize again for the delay. My name is Zachary Everett. I am not in the technology department here at Daikin Applied, but I am familiar with the ventilation products that we have, and I'm going to begin to move forward right away because I know that we're about a minute behind schedule. So today we're going to be discussing ASHRAE 62.1 ventilation standard and the way that we calculate our ventilation rates for all jobs that are not in-person inpatient healthcare. So this is something that is going to be broadly defining a lot of our DOAS units, something that we've been doing since 1981 the same way, and it's something that ASHRAE has begun to focus on quite a bit here in the last couple of years. The broad definition, I'm going to start kind of from the beginning, and I apologize if this is repeat information for some of you, but I want to kind of take us all the way through from the inception of the 62.1 code all the way through where we stand today. So ASHRAE defines 62.1 ventilation as air that has no known contaminants at harmful concentrations, and where a substantial majority, it's 80% or more, of participants or folks in the space do not express dissatisfaction actively. So that's a very broad definition. And it's allowed us a lot of flexibility through the years in making our calculations, but it's something that hasn't really been in focus until more recently in the COVID era, when indoor air quality really became something that was at the forefront of our discussions. So there have been three procedures for calculating our ventilation rates. And I mentioned that these came to be in 1981, though they were not actually enforced until the early 2000s. On the left-hand side, we have the ventilation rate procedure. This is something that the vast majority of us are going to be comfortable with. It's going to be the CFM per square foot, the CFM per design occupant, and the type of space that we're operating in. So that's the prescriptive method. It's something we've got calculators for. It's something we've all done many times. On the right-hand side, we've got the natural ventilation procedure. So this is operable windows. It's no longer how we're designing our buildings, but it's something that for a long time, we just said, crack the window, problem solved. In the center there, we've got the indoor air quality procedure. And this is something that has not had a lot of clarity through the history of the ventilation code. And it's something that we, for the most part, have not really focused on over the last 30 years or so. So on the left and center there, we're going to focus on the ventilation rate procedure and the indoor air quality procedure for the remainder of the presentation. It's really where we see most of these calculations going as we move forward. So I'm a visual person. I like to put these two diagrams on the screen and help to compare and contrast the existing procedure or the legacy procedure and where we really see the industry moving. On the left-hand side, we've got our traditional means of ventilation. Bringing in outdoor air, regardless of the temperature of that air, and we're conditioning it to neutral or some sort of comfort temperature, 70 degrees or so. We're dumping it into the space. And the idea there is that we're going to be displacing some of the existing air and exhausting from toilets and variable exhaust from kitchens and everything else. We're going to be exhausting some of those contaminants out. So this is dilution ventilation. So the kind of mantra you may have heard in the past is the solution to pollution is dilution. That has been how we've designed for the vast majority of the history of ventilation code. Unfortunately, that means that if we want to improve, not just keep the status quo, but improve the indoor air quality that we have in our spaces, we have to bring in more air to do that, and we have to exhaust more air. And you say, wait, we have energy recovery wheels. Isn't that effective? Yes, it helps certainly, but we're still treating that air, even though we've captured some of the air, heat or cool, even latent energy. We're still having to condition that outside air at its extreme temperatures. And so there is a better way, and it has been in the code. It comes in the form of this indoor air quality procedure, but we weren't focusing on that procedure for the vast majority of our history because it was not clearly defined. And that means that all of the onus or the L word liability fell on the design engineers. That's not how we operate in this industry. It's customer first. We are doing this for the sake of our end user, but we don't voluntarily take on liability. And so that's not something we focused on directly. However, in 2022, we got a great deal of clarity from ASHRAE regarding the portions of that procedure that are on the bottom right-hand side of the calculation there. So the emissions rates were clearly defined. By emissions rates, I mean that fresh paint smell when you walk into a brand new space, that's formaldehyde. There are a series of these volatile organic compounds, VOCs, that ASHRAE has identified. There are 14 as contaminants of concern. So those emissions rates, what's being off-gassed into our spaces, that's now defined by ASHRAE. The concentration limits, they're in the denominator of that calculation, also defined by ASHRAE. And it's not something that we knew before. So it was on the design engineer to tell the end user and ASHRAE, the governing body, what it was that they were designing to. That's all clearly defined now in an addendum published by ASHRAE in 2022. And lastly, we have that box in red, the cleaning effectiveness. This is something that we used to rely on manufacturers for, and it's now something that can be done in third-party testing labs. So when I say cleaning effectiveness, what type of cleaning am I talking about? I'm not talking about 13 filters and equivalent air changes in that sense. I'm not talking about ASHRAE 241 pathogen mitigation air cleaning with like UV lights, UVC lights. Instead, I'm talking about gas phase air cleaners. Gas phase air cleaners are actively removing, by the process of adsorption, all of the 14 volatile organic compounds that ASHRAE has identified. They're removing them from the return air pathway, and therefore allowing us to put that return air back in as, quote, fresh air, rather than relying 100% on our outdoor air as the source of, quote, fresh air. So we're no longer just diluting the air in our spaces. Instead, we're actually providing fresh air, quote, actually fresh air that's actually had the 14 volatile organic compounds removed from it back into the space for our indoor air quality. So this is a little bit of a shift, right? So we're going to reduce the volume of outside air. And one of the questions that I often get at this phase is, can we reduce it down to zero? They do that in submarines. They do that in a lot of different applications. Is that something we can do in our industry? In most cases, no, because we still have exhaust air. We're not treating all of our air. We're still exhausting, so we have pressurization requirements. But short of those pressurization requirements, yes, we can remove almost all of the outside air in theory. In practice, that's not always the most fiscally responsible move, right? So this air cleaning does cost money to put in, and there is a break-even point at which it no longer makes sense to create, for example, the cleanest air in the world, because beyond a certain threshold, this isn't making a difference to the end user or the occupant specifically. So that's the introduction. I do want to pause, and Travis, I'm not able to hear the group, so if there are questions, I will address them at the end. I apologize.
No, you're good, Zach. Keep on trucking, bud. We're doing great. Thank you.
Just making sure I communicate. Okay, perfect. So we've introduced the concept of ventilation rate procedure, as well as the indoor air quality procedure and the differences between them. I think it's helpful to visualize them in a different way here. As we talk about indoor air quality as a whole, ASHRAE actually put out a position paper that said CO2 is not the best means of measuring indoor air quality. Instead, we should focus on these VOCs, these 14 contaminants of concern. And so when we do that with the dilution ventilation style of calculation, we're having to bring in more and more outside air in order to improve the indoor air quality, because we're having to exhaust the equivalent amount of outside air. So on the left-hand side of the screen, we've got the outdoor air ventilation on the y-axis and the better indoor air quality on the x-axis. And so this very clearly shows the more clean air we want to have in our spaces, the more outside air we need to bring in order to accomplish that. And in our real world, that means we've got to process that air, which means we've got a serious concern from an energy perspective. I live in New York City, where we've got electrification push that is very, very strong. We're in fact being penalized to the tune of $268 per metric ton of CO2 we produce over a certain threshold. I know that in your market, the electrification push is very real as well. So this is a huge problem for us as we start to look at the indoor air quality being such a driver and our requirement to bring in more outside air in order to accomplish that goal. We also have wildfire smoke coming down from Canada, and I know all too well that you guys have similar issues with consistent outdoor air quality as well. So on the right-hand side, we've got that minimum outdoor air ventilation for the purpose of pressurization. And then we've got the source control and removal bar, which we have full control over. So as a design engineer, I love having control over the air that I'm actually yielding within the space without relying directly on increasing the amount of energy being used to accomplish the goal. So that's what this chart, I think, does a good job of illustrating. We can introduce more and more of this air cleaning technology in order to accomplish that goal rather than bringing in more outdoor air. So what does that look like? Well, we have sorbent material. It's something, if you are able to see my camera, I'm holding up an example here. It's just a white granular powder. That sorbent material is packed into a series of filters. They look like this. They are 1-inch filters, and that sorbent material is packed within these filters. These are stacked in series, which I'll talk about in just a second, but we're actually then going to be adsorbing directly the 14 VOCs that are identified by ASHRAE, and passing through this material will be all of the standard products, so nitrogen, oxygen, water. We don't have any harmful byproducts of this adsorption. Instead, we're just removing from the return airstream the contaminants of concern. You'll see on the right-hand side there, we've got a module that's located on the outdoor wall of our DOAS unit. I'll explain why it's located there, but that's where that sits. It sits in the return airstream, and then the resulting clean air is passed directly into the supply airstream. I do have a quick quote. I'm not going to read it, but ASHRAE has identified this type of technology and this means of calculation. It's in the user's manual. It's in a series of resources that I'll make available to you at the end of the presentation. I think it's important to validate anything new in this industry, so I want to put a couple of references to ASHRAE. That's the governing body. This is not something that's coming from Daikin or a third party. This is coming directly from our governing body. So I mentioned our modules that have our sorbent filters are going to be located in the return airstream. They're also located against the outside wall, and they're processing 1,000 CFM of air through them at any given time. The yielded equivalent air, so if we were to say how much outdoor air would we have to process in order to have something similar to this type of technology, it would be about 2,000 CFM per module. And those modules are located, I mentioned, on the outdoor wall of our DOAS units. On the right-hand side is the reason for that location. So we have the ability with this type of technology to regenerate the sorbent material that we're using. And when I say regenerate, I mean we heat air up and we pass it through the sorbent filter to expel the carbon dioxide that has been captured by the filter out into the environment. So we have to locate this on the outside wall because there is an outdoor air damper that is controlled by an internal control panel that opens, and the fan on board, which again is existing in the module that is produced by Daikin and put into the units directly, that onboard fan overcomes all the static that's associated with the 12 filters that are inside the module itself. The onboard controller opens your outdoor air damper, and during this regenerative mode, we have about 300 CFM of air passing through the unit itself. So just as our rules of thumbs and takeaways, in the regenerative mode, we have 300 CFM passing through the unit. That's being expelled, so you shouldn't have pressurization concerns. In our standard operation, we have 1,000 CFM of air, and the equivalent outdoor air is about 2,000 CFM. Daikin can put between 1 and 6 of these modules in various types of equipment, whether it's a packaged rooftop with 2 modules or an outdoor air handler like the Skyline air handler that we offer with up to 6 modules. So the equivalent outdoor air reduction would be about 12,000 CFM while yielding the same or better indoor air quality with a significant reduction in energy requirement to do so. Just walking through each of the components, I mentioned the fan to overcome the static, the onboard heater. Both of those parasitic loads are taken into account when Daikin and Inverid are assisting with payback calculation for your particular application. I will offer for you to reach out directly to your long representative. They can assist you with the indoor air quality procedure calculation as well as those payback calculations for any application you think might be viable. When we talk about this type of technology, recommend the technology be implemented in areas where there is a high people load and where there is low exhaust. So in a place like a concert venue or in a gymnasium that fills up to full capacity very quickly, and we have to design to those full loads, this is a great technology that'll save both upfront cost and operating costs down the road. This is also great in areas like the ones that we both live in, where the design temperatures are pretty extreme, both in the summer and the winter. And in areas where energy is expensive, it also pays back very quickly. So schools, office buildings, we're happy to do the analysis anytime to make sure that this is a viable solution for you, and Long is going to be your partner in that calculation. I do have there on the right-hand side the QR code. I mentioned that we were going to provide all the resources to the material we went through today. This is material that's available in the public domain from ASHRAE directly. They will also have the calculator for the IAQP method, and I will update the QR code accordingly. And lastly, sorry for the delayed start here. We're just getting our technology in order. If there's anything that I can do, my email address is there. Thank you very much for your time and attention, for sticking with us here. I'm going to pass it back over to Travis.
Thank you, Zach. I appreciate it. Thank you all for your patience. Next week, we will be doing, Sean Davenport Smith will be presenting Link Aegis, which is North America's first commercial CO2 heat pump water heater. So please join us for that. Zach, thank you very much for all of your time, and I hope you all have a great day.